Okay, how do you solve that equation? You've seen that kind of equation before somewhere, I bet. Solve for x. Now, the way I like to look at equations often is I like to look at it kind of verbally. X is some mystery number that we want to know. It says that number squared. In other words, when you take some number times itself, you get 9. Now just ask yourself, what number times itself is going to be 9? There's two answers, right? What number times itself gives you a positive 9? Well, x could be positive 3, because if you take a positive 3, multiply it times itself, you get a positive 9. But x could also be negative 3, because if you multiply negative 3 times negative 3, you also get positive 9. So in other words, 9 has 2 square roots. Let me actually, you know what, I think I'll write that over here. 9 has 2 square roots, if you want to be Minnesotan about it. 2 square roots, plus 3 and minus 3. So there are 2 solutions to this equation. If x is some number, and what I know is that when I square it I get 9, well, x, there's 2 possibilities for x. It's either plus 3 or minus 3. Now usually when we write this out loosely, we say things like, oh, take the square root of both sides. But remember how we usually write this? We put that plus or minus in front of the radical symbol like this. X equals plus or minus radical 9. And when you say radical 9 is 3, well, you've got this plus or minus here telling you that you've got 2 solutions. X could be plus or minus 3. Now that may have kind of snuck by you there, but putting the plus or minus there is actually very important. And why? Well, if you look at this equation, or it's not an equation, it's an expression. If you look at this expression, radical 9, this is positive 3 only. This is not a plus or minus 3. It's just the positive 3. So that's the first thing I kind of want to get across, is that the radical symbol by itself indicates the principal square root. And principal square root means the positive square root. So every number's got 2 square roots. One's positive, one's negative. You know, so like square root of 9, one's positive, one's negative. It's either plus 3 or minus 3. Well, this symbol here says I want the positive one. Just give me the positive one. Okay, so keep that in mind. This symbol itself, you're going to hear me say square root of 9 all the time, but really this should be pronounced radical 9. Pronounced, not pronounced. Pronounced. Radical 9, or if you want to be real good about it, you will pronounce it as principal square root of 9. Radical 9, or I'm going to put that down because that's really the best. Principal square root of 9. So when we're playing with these symbols, you got to keep that in mind. This symbol by itself is only indicating one of the square roots, the principal square root, the positive square root, and only that square root. Okay. When you're solving an equation, just to look back here one more time, when you're solving an equation like this and you say, oh, I kind of need to take the square root of both sides, you have to put the plus or minus here, because if you don't, this symbol is just 3. You put the plus or minus there as a way of saying, no, I want both roots. I actually want the both square roots of 9, not just the principal root. I want both roots, plus or minus. Okay, so hopefully I've kind of got that point across. So without the plus or minus in front, this symbol just indicates the positive root. Got it? Got it? I'm trying to erase that part. Anyway, whatever. All right, let's, in the name of continuing part A, the proper handling of this radical symbol. Okay, now you've been sort of alerted that the radical symbol only means the positive square root. There's something else I need to show you here too. It's a misconception that a lot of people have that I need to make sure we don't fall for it. So, first of all, would you believe that if I wanted to simplify this expression, radical 3 squared, that I would get 3? Do you believe that? Well, you're right. It's 3. It's 3, and it's 3 because what you've got is radical symbol. You do this, 3 squared is a 9, and then you ask the question, what times itself is 9? And the answer is 3. You get 3. So what I have to warn against is you don't want to say that this radical symbol cancels the square. It doesn't quite work that way. And to show you that it doesn't quite work that way, here's a radical symbol, here's a square, right? If the radical symbol really did just cancel the square, this would come out to -3, right? If that's really what the radical, but it doesn't. This is also equal to 3. Why? Because you have to first, get this out of here, you have to first finish what's inside here. I've got a -3 times itself, and a -3 times a -3 is a 9. And then you take the principal root of 9 and you get a +3. Okay, so it might seem like a technicality, and it kind of is. We're being very careful interpreting these things, but you want to avoid this idea that a square root simply takes a square off. It isn't quite that simple. Now, here's where people usually make the mistake of thinking that a square root takes a square off. See right here? Square root takes a square off. If that's what you're thinking, then you're thinking, oh, radical x squared, that just equals x. And the problem is that that ain't necessarily so. That ain't necessarily so. This is only true if x is a positive number. I'll prove that to you just by referring again over to these areas. See, when x was a +3, you did get a +3 as your answer, right? Maybe I'll do it this way. X was +3, right? X was squared. X was +3 being squared, and when I took the square root, I got a +3. So x in, x out, it worked. But here on this one, if you used x was -3 and squared it, well, the square root's going to be 3. It's not going to be, this is not a -3. In other words, you cannot simply say that a square root cancels a square. It doesn't work that way. It does not work that way. So what are we supposed to make of this then? Well, like I was saying, if we happen to know that x is positive, if we happen to know for sure that, oh yeah, that was a positive number, that was like a +3, oh yeah, then it works. Then it works. So you'd have to say that if x is positive, then it works. Okay? Well, what if it isn't? Otherwise, we could say this. Let's say that x was a negative number, and here's an example of x being a negative number. When x was -3, we squared it, we took the square root, we ended up with +3. See, the thing is, you always end up with a positive answer. You have to, because this symbol means principal or positive root. It means positive root. You have to get a positive answer. And so back to the problem, what if the number that was squared was a negative number? Well, I'm supposed to get a positive answer. Well, here's how you do that. You put it in an absolute value. That way, if I used, for example, a -3, if I put a -3 here, I'd have the square root of 9, or excuse me, radical 9, which is a +3. But then again, that's also a +3, right? This is +3. And so this statement is actually true right here. So if you know that x is positive, then you can write this. Radical x squared is equal to just x. Otherwise, you have to put these absolute value bars on there and say radical x squared is actually the absolute value of x. Once more, this radical symbol is telling us, principal or positive root. You have to have a positive answer over here. So since you have absolutely no idea what x is, it could be positive, it could be negative, using the absolute value bars hedges your bets to make sure that you really do have a true equation that you're looking at here. Okay, so you got to keep this in mind. Got to keep this in mind. Square root of x squared. Yes, it's x if x is positive. Otherwise, you really should put the x in absolute value bars, just in case x is negative. If you know, You know, in a lot of, just while I'm here, a lot of the algebra textbooks out there, what they'll do is they'll give you a whole bunch of problems that say, assume x is positive, or assume the variable is positive. And they don't really tell you why you're assuming that, or they don't really pay much attention to that. So I'd rather just not assume that it's positive. Let's not assume that it's positive. Let's use the absolute value bars. Let's keep in mind, and this will actually be important later in the course too, let's keep in mind that a radical symbol indicates the principal or positive root only, and that therefore a radical x squared, if we don't know whether x is positive or negative, we should really put it in the absolute values like this. Okay. Well, I hope you don't have to pause and rewind that too many times. So that's part A. That was actually, I think, the hardest part, was getting across the radical symbol. It's you got to be careful when you're using the radical symbol. There's a lot of meaning. There's a lot of things going on out there when you write that seemingly innocent-looking radical symbol out there, right? So be careful with that thing. Pardon me. A double. Woo. Woohoo! Okay, so now let's get on with the main business, which is going to be simplifying radical expressions. So this is the main rule we're going to keep using. I call it the factoring rule. I don't really know if it's called that or not, or I've never seen it called anything. So I'm going to call it the factoring rule. What's the factoring rule? It says that, for example, take a look at this and tell me if you can, or see if you can figure out why that would be true. It says that the square root of 25x really does simplify as, notice I got a 5 here, I still have the square root of x, radical x. So somehow this 25 on the inside became a 5 on the outside. See how that happened? Radical 25 gave me a 5 on the outside, and then the radical x is inside, and the radical x is still inside. Do you see what's going on? You might see what's going on and not have any idea why I'm calling it a factoring rule. Well, I'm calling it a factoring rule because when you have radical 25x, which is basically two things multiplied together, you can think of it this way. Radical 25 times radical x. That's called factoring. I broke it apart into two different square roots that are still multiplied, right? So this is useful because this is something that you can do, and this is where the simplifying comes in. Simplifying radical 25 gives you just 5. Now you can't simplify radical x, so you just leave it. But that's how you're getting at this 5 radical x. So instant replay. I had a 25 and an x both inside. I can say I got a 25 inside times, and I got an x inside. But wait, 25 inside a square root symbol type thing, that becomes just a 5. Just a 5. I don't need the square root symbol anymore. That's where the simplification is happening. There's no more radical there. 5 radical x. So this is the main kind of sequence that we're going to be following today, is we're going to be breaking things apart, trying to take square roots where we can, and leftovers are going to be left inside the radical. Take a look at this one. Do you believe that's true? How would anyone have turned, well, the x is just staying in the inside, so I guess that's that part we can follow. But somehow the 75 here is becoming, well, we got a 5 here and a 3 here. How's that happening? Well, I'll show you how it's happening. What we're doing is we're thinking of the 75 as having a 25 in it. So 75 is like a 25 times a 3 times an x. Okay, so I've got a radical 25, and then I've got a radical 3, and I might as well put the x with it right now. And so the radical 25 is a 5 out front. And you don't have to do the steps precisely like this. This is just me kind of thinking to myself, really. I say, oh, that's 75. Yeah, it's got a 25 in it, and I know that I can take the root of 25 to give me a 5 that's outside the root, because I took the root. Get it? I took the root of 25. So it's not in the root anymore. It's outside. It's a 5. It's a regular 5. The 3 and the x, I can't take the square root of a 3 or an x, so that's just going to have to be stuck staying inside there forever. Okay, that is what I mean by the factoring rule. Break apart rule is something I've used to call it too. But this is the basic idea. When you've got a big old radical, something like a, 25x, something like a, 75x. You want to try to find something square rootable that you can pull out. And so part C here, what you're hunting for is perfect squares. A 4, if you had a factor of 4, that'd be cool because you could take the square root of 4 and get a 2. 9 would be cool. If you find a factor of 9 inside your number, you can take the square root of 9 and get a 3. Simplify it. 16, that'd be a cool factor. If your number is something times 16, you'll be able to take the square root of the 16, and so on. Here's a 5 times a 5 is 25, so if you have a 25 in there, and so on. So what you could do is you can take, like, for example, this one, 12. That's a 12. Radical 12. Now, 12 is, somewhere around here on the list. I usually start there and I go backwards. So I say 9. Does 9 go into 12? 9 does not go into 12, not evenly. How about 4? Hey, 4 goes into 12. Cool. So what you do is you break up the 12 as a 4 times 3. Or to be precise, radical 12 is radical 4 times radical 3. Again, I sniffed out a perfect square. The 12 has a 4 in it. Sniff it out, break it apart, because now this part simplifies. Radical 4 is just 2. Square root of 4 is 2. And then this is not square rootable, not evenly. And so we've got 2 radical 3. And by the way, if you ever wanted to, get out your calculator or something, hey, I got a calculator right here. Watch this. You ready for this? This is going to be great. I'm going to take the square root of 12 and I'm going to hit equals, and it's going to tell me that it's about 3.4641 if I just go to 4 decimal places. Now I'm going to take this and enter that on my calculator. 2 times the square root of 3. Yep. And when I enter that on my calculator, it's telling me 3.464. See? They're the same to at least 4 decimal places. They're the same. It works, by golly, it works. So here's a bunch more examples we can try. So let me erase this stuff. I said erase. Okay, let me erase this stuff. I got an 18 here. So 18 is, it's between 16 and 25. Now 16 is not going to divide into 18 evenly, but I can try 9, and 9 goes into 18 evenly. So I'm in business. So you think of the 18 as a 9 times 2. In fact, you might just, to be easy, write it this way. 9 times 2. 18 is 9 times 2. Cool. So this is square rootable. Radical 9 is 3. And then the 2 is just sitting there. It just schleps along like that. Okay? So break up the 18 as a 9 times 2. How about the 20? What can we break up the 20 as? Well, I think 4 is going to be your best bet there. So you think of the 20 as a 4 times a 5. And again, really, this is radical 4 times radical 5. The simplifying happens right there because radical 4 simplifies to 2. And so we've got 2 radical 5. These are fun. These are fun. Hey, you want to pause and try all 3 of those yourself real quick? See how fast you can do them. Try using this little list I've got up here. I like using this list. You back already? Okay, cool. So I got the 24. So I'm looking at my list and I'm saying, well, 16, no, 4. It's just a 4. Well, if that's all you get, that's all you get. Got to get something, right? Or you hope to get something. So I'm thinking of the 24 as 4 times 6. So radical 24 is really radical 4 times radical 6. Radical 4 can be simplified. That's the whole idea. You want to be able to take a square root somewhere. So radical 4 is 2. And then radical 6 does not come out even. And so there's your answer. Cool. Looking at the 27, did you see a 9? 27 has a 9 in it. So you think of the 27 as a 9 times 3. So really I'm taking radical 9 times radical 3. Radical 9 can be simplified. What times itself is 9? 3 times itself is 9. Remember, the principal square root of 9 is 3. So 3, that's a 3. And then this is still there. So this is 3 times radical 3. Cool beanies. 48, what do you see? What do you see? Well, if you leave the calculator in the drawer for like a semester, I think you'll be impressed at how much better you are with numbers at the end of the term. It's just an invitation. But 48, you might, if you're good, First of all, I'm looking up this list and I'm saying, well, 48's up here somewhere. Right now, obviously, 36 doesn't go into 48. Very nice. 25 doesn't go into 48. Very nice. But what about 16? 16 goes into 48. Really nice. 16 times 3 is 48. So I'm going to split this apart as a 16. So radical 48 is the same thing as radical 16 times radical 3. But the radical 16 simplifies to just a 4. And the radical 3 does not simplify, so the 4 is still multiplying the radical 3. Cool. Now, I'm going to actually do that one over a different way, just to make some. This is worth pointing out, I think. Sometimes, sometimes you might like not see the 16, but you did see the 4. So you say, oh, I got a 4 times a, what would that be? 4 times 12. Woohoo! But what you want to do here is you want to say, wait. The 12 also has a 4 in it, see? So break up the 12. Keep going, in other words. So I got a 4, I got a 4, I got a 3. 48 is 4 times 4 times 3. So I've got a radical 4, a radical 4, and a radical 3, all multiplied together. The radical 4 is a 2. The radical 4 is a 2. The radical 3 is a radical 3, all multiplied together. And so what I've got is a 4 radical 3, which is the same answer as we got the first way. Okay, so if you want, you can actually, sometimes I call this the tree method or whatever. You can just kind of, break it up like that if you want. Make a little tree, break it up. Whoops, I saw a 4, so I went for it. And then I went, oh, wait, there's another 4. So you'd have to keep going until you got all the 4s out. And then make sure that 9 doesn't work and all that other stuff. Will you stop blipping on me, you dumb thing? Okay, now these numbers are just a little bit bigger. It's worth taking a look at some bigger numbers. If you don't feel like going through this particular list of perfect squares, it's definitely my favorite method, but a lot of people like this method better, so it's worth, got to show it to you at least. So what they'll do instead is they'll do what's called prime factorization. Prime factorization means you're going to divide by 2, by 3, by 5, by 7, by 11. Get it? Those are the prime numbers. And you always start with 2, and you divide by 2 over and over and over and over until you can't anymore. And once you're done dividing by 2, you try dividing by 3, and you do that over and over and over again until you can't anymore. And then you would try dividing by 5, and you would do it over and over and over again until you can't anymore. Do you get the idea? And then you would move to 7, and so on. It's kind of, sledgehammer comes to mind at the moment. It's kind of the sledgehammer approach. I see a big number. I'm going to sledgehammer that sucker. First, I'm going to start by dividing by 2. Can I divide 72 by 2? I sure can. That would be 2 times 36. Keep going. Can I divide 36 by 2? I sure can. That would be 2 times 18. Keep going. Can I divide 18 by 2? I sure can. That would be 2 times 9. Ooh, and now look at the 9. Technically, that would break up as a 3 times 3. So what I got here, these are all prime numbers, right? So the 72, and all of a sudden I'm going to have to move this. It's kind of getting in the way. Shrink yourself. Oh, come on. Sucker's touchy, man. Shrink yourself and move over. Okay, so trust me on this one. The 72 became a, what have I got? A 2 times a 2 times a 2 times a 3 times a 3. So every time I get a pair, here's a pair, I'm going to write it as a 2 squared. And then here's another pair, a 3 squared. And then here's a 2. Okay, so you can think of it as these 3 radicals all multiplying together. And even though we saw that that's not quite correct to think of it this way, square root taken off the square, it is true that radical 2 squared is 2, radical 3 squared is 3, and then this is a radical 2, and so this is all multiplied, and so 2 times 3 is, I got a 6 times a radical 2. So you can do the prime factorization. You break the 72 up into all its little prime pieces, and then you gather together 2 at a time. Every pair is going to be simplifiable. A radical 2 squared is just a 2. A radical 3 squared is just a 3. Every time you get a pair, you want to separate that out into its own square root, or its own radical symbol. Let's change colors and do this one. 96. Start busting it up. Divide by 2. It's 2 times 48. Divide by 2. That's 2 times 24. Divide by 2. That's 2 times 12. Divide by 2. That's 2 times 6. Divide by 2. That's 2 times 3. You bust it up until it's all primes. So I guess I usually circle all these numbers, but I guess what you could do is you could say I broke up the 48, I broke up the 24, I broke up the 12, I broke up the 6. Okay, here's what I'm left with. What are you left with? You're left with 96 equals. Every pair should go into its own radical. I got a pair of 2's. Oh, there's another pair of 2's right there. And then, oh, I don't have any more pairs. Might as well just put those back together. 2 times 3 is 6. So notice that you've got radical 2 squared is 2. Radical 2 squared is 2. Radical 6 is what it is. And so your final answer is 2 times 2 is 4. Radical 6. And that's what you get for that one. Okay, we're going to have to shrink this too. Shrink. Move. How many shrinks does it take? Shrink. Come on. Why do they make these touch screens so finicky? Okay, that's cool. Cool enough. I think I should pause here and let you tackle that sucker. Pause, come back, tackle the sucker. All right, 294. We're going to do this by prime factorization, which means I'm going to start by dividing by 2. 2 goes in 147. Well, I guess I'm done dividing by 2 now because that's an odd number, right? Can't divide by 2 anymore. I guess it's time to start trying the 3. Will the 3 work? The 3 will work. Do you know that shortcut? There's a shortcut. You add the 1 plus the 4 plus the 7 together in the 147. You add the 1 plus the 4 plus the 7. That gives you a 12. 12 is divisible by 3. And since 12 is divisible by 3, I know that the 147 is divisible by 3. So this will work. Now, what do you get? Well, 3 into 14 is 4 times would be 12, so that's 2 left. 27. 3 into 27 would be 9 times. Oh, look at that 49. I can tell right away that's a pair of 7s. So what we got here then, the square root of 294 is, there's a pair that I can put together. And then these do not have any pairs to go with. I'll just put them back together. 2 times 3 is a 6. And so what we've got here is a 7 times a radical 6, because radical 7 squared is just 7. 7 radical 6 is how you simplify that one. All right, we're moving now, folks? So that's numbers. That's all dealing with numbers. Now we got to start playing around with some x's, some variables inside of our radicals. So let's kind of try to make a border here. Okay. Now we got x's inside. Well, what's this going to do to us? Well, I invite you to think here, and there's many different ways you could do this, of course. But one way you could think about this, maybe I'll make this verbal question, right? What times itself gives x to the 4th power? Well, it's got to involve x's in some way, right? X to some power, and then you multiply it by itself, and you're supposed to get x to the 4th. Now, do you remember in a situation like this, that's supposed to be a big multiply there, in a situation like this, we're multiplying a couple of x things here together, what you do with the exponents? Like if this were well, let's put it this way. What would happen if I had just x times x? You think of it as x to the 1 times x to the 1. You add the 1 and 1 to get 2, right? X to the 1 times x to the 1 is x to the 2. What if you had something like x squared and you multiplied it by itself? Well, x squared times x squared, you would add the 2 and the 2 to get a 4. So you know what? Looks like we just found our answer. What times itself gives x to the 4th? The answer is x squared. So I'm going to actually cancel this off right here, or erase this off, and say x squared. X squared times itself. Notice if you want to look at this as a real shortcut, the 4, I basically cut it in half. Cut the exponent in half. And why does that work? That works because if you want it to add up to x to the fourth and you have to spread it out into two spots, well, you take the 4, you cut it in half to get a couple of 2's. X to the 2 times x to the 2, the 2 plus 2 is 4. That's why it works. Now, if you trust me, you'll look at radical x to the 6th and go, are you saying I should just cut the 6 in half? And I'm saying, yeah, you should just cut the 6 in half. So this is going to be, oops, not radical anymore. We're simplifying it. So radical x to the 6th becomes just x cubed. And why is that? That's true because x cubed times itself would give you, you'd add the 3 plus 3 to get a 6. Okay, cool. Now, what about this last one over here? X to the 12th. Are you telling me that we should just divide the 12 in half? And I'm saying yes, I'm telling you that. Because, again, if you took x to the 6th times itself, you would add those two exponents, 6 plus 6, and you would get 12. Okay. Now, looking back on all three of these right here, I did make a mistake, and I wonder if you can spot it. It's a subtle mistake, and it has to do with what we did right away on page 1. Let me go back to page 1 for a second. You ready? Where are we? Here we are. Back on page 1, we were saying that the principal root has to come out positive. Let me just write it in those terms. I'm just going to write it just like that. The principal root of anything in the world, the principal root of anything must be positive. It has to be. That's how the symbol is defined, the principal root, the positive root. And we saw over here again. If you put a negative 3 in there and you square it, well, you're not going to get a negative 3 when you take the radical. It doesn't happen. Because first you square it, it becomes positive, and then you take the principal root and it stays positive. So anyway, the principal root of anything is going to be positive. It is. It really is. Looking at these answers, the principal root of this should be positive. Is x squared positive? Yeah, it's always positive. Even if x is a negative number, you square it, it's positive. No mistake there. How about x to the 12? When I took the radical here, I got x to the 6th. Is x to the 6th positive? Yeah, always, right? You raise anything to an even number, it's going to be positive. So even if x were a negative number, you raise it to an even power, it's going to go positive on you. So yeah, that's fine. But, is this always positive? That's not always positive. Because if x is a negative number and you cube it, it comes out negative. So, spaghetti-o, we should have gone like this. Absolute value of x cubed. Okay, that's the real answer to that one. The absolute value of x cubed. Which, as you know, if x is positive, then of course this is going to be positive, whether or not you take the absolute value. But if x is negative, you need to take the absolute value to make it positive. So just put the absolute values there. Okay, so always check for that. Check for that. So I'll write this down one more time. Radical indicates positive root always. X cubed is not going to be positive if x is negative. So I put it inside the absolute values bars to take care of that. Okay, let's come up. Let's see, what do we got? We got 3 more here? Okay. What do we got here? Radical x to the 5th. Well, I was saying something about cutting the exponent in half. Here's the problem with that. If I cut the exponent in half, 5 cut in half is a 2.5. That's no good. So what you got to do, really, is you got to think of this as x to the 4th times x. Like that. Okay? Take the closest even number. The closest even number is 4. So I take x to the 5th and I split it off as an x to the 4th times an x. The closest even number is 4. Now, why am I doing that? Because this part here is simplifiable. You just cut the exponent in half. And then this part here is not simplifiable, so you just copy it. And there we go. Quick check. If x is a negative number, does this still come out positive? Yes, it still comes out positive, so I don't have to use absolute value bars anywhere. That is how it simplifies. How about this one? This is a good one to be alert to, because notice you've got the 9 to play with, and then you've got the exponent of 9 to play with. Well, playing with the 9 itself, that's pretty cool. It's because you can take the radical 9 right away. So that's not going to take any special treatment, right? But this is going to take some special treatment. Please remember, you do not take the square root of an exponent. You don't say, oh, radical x to the 9th is x cubed. No, you don't take the square root. You do this. The closest even number in this case is an 8. So I take that x to the 9th and I split it into two parts, x to the 8th, x to the 1. Okay. Now, I can simplify some of this stuff. Radical 9 is just a 3. Radical x to the 8th is, cut the exponent in half, x to the 4th. Radical x I cannot simplify, so just schlep it along like this. And there is your answer. Is this always positive? Yes, it's always positive, because x to the 4th is always positive. And that symbol is always gives you a positive result also. So we don't need any special absolute value bars there. Want to try this one? So you have to handle the 20 and the 7 separately. So as far as the 20 goes, I'm thinking, it's got a 4 in it. 20 is like a 4 times 5. So let me write this out kind of neatly then. So I'm going to think of the 20 as a 4 and a 5, right? The 4 will be simplifiable. Radical 4 is simplifiable. I'll do that later. Meanwhile, for this x thing, the closest even exponent is 6. So I'm going to take x to the 7. I'm going to split it up as x to the 6 times x. Now, I've got it all spread out. I do the simplifying parts. Radical 4 is just a 2. That does not simplify. Cut the exponent in half. That's x cubed. That does not simplify. Now let's put this all together in order. Put the 2 first, put the x cubed next, and then these, a 5 and an x, they're both inside, so you can just put them both inside like this. Finally, will this always be positive? No, it will not, because if x is negative and you cube it, it's still going to be negative. So what does that mean? It means we have to do one extra thing, and that's put it in absolute value bars like this. Okay. I think we've simplified a bunch of radicals, huh? Yes, we have. There's one more thing we got to look at, and it's called simplified, well, the one more thing we got to look at really is down here, and it's rationalizing denominators. And maybe what I'll do is I'll come back up to this part F in a minute. Let's come down here and say, what are we doing? What do we do with a thing like this? Radical 2, you can't simplify radical 2, and you know what? You're right, you can't simplify radical 2, but we do not accept radicals in a denominator. It's etiquette. It's good form. We do not accept radicals in a denominator. 1 over radical 2 in the denominator? How dare you? A radical 2 in the denominator, that is bad form. So we've got to fix it. The question, of course, is how are you going to fix it? Well, there's a nice little trick, and it works splendiferously. You'll like it. I'll just show you how it works. Multiply top and bottom by root 2. Right? You can do this. This is the old how to change the way a fraction looks without changing what it equals trick. You multiply it by something, same thing, top and bottom, right? So this is certainly a legal move. And what it does for us is up top, 1 times radical 2 is just radical 2. But on the bottom, look what I got here. I got a radical 2 times a radical 2. Well, that would be a radical 4, which is a 2. And so you end up with a radical 2 on top and just a regular 2 on the bottom. And so this is okay. This is not okay. A radical in the denominator, not okay. A radical in the numerator, who cares? As long as the denominator does not have a radical, we're happy. And this is something called simplified radical form, which again, I'll get back to that in a little bit. But that's your basic trick. You got a radical in the square root radical in the denominator. Do this trick. Works pretty much every time. I'm trying to think of a time that it doesn't. I can't think of a time that it doesn't. Works every time. This one. We don't like having radicals in the denominator. Radical 3x? Huh, no good. So, duplicate it. Multiply the top and bottom by radical 3x. Now, what does that get me? Well, on the top, 1 times radical 3x is what it is. And on the bottom, now you can write this out if you want, but you don't really have to. When you take the radical times the radical of the same thing, it's just the radical's going to go away. So again, the part that I'm hiding here, or the part that I didn't write down, is that when you multiply the 3x times the 3x, you get a 9x squared inside of a radical, right? And then you take the square root of 9, you get a 3. You take the principal square root of x squared, you get an x. Okay, cool. So that works pretty good, right? Works pretty good. Now, are you asking yourself, how do I know that this is positive? Well, you don't. So you better put this in absolute value bars. You can put the whole thing in absolute value bars if you want, but I think it's enough just to put the bottom in absolute value bars, because again, this symbol up here means positive root. So that's, whoops, that's not a problem. So you need the absolute value bars here. You need those. Let's do some more. How many more we got? 1, 2, 3, 4, 5, 6. Oh my gosh. Okay, we got a few. So looking at this one, x, and then we've got this radical 2x on the bottom. Well, that's the part I don't like. So multiply top and bottom of radical 2x. So the top is giving us well, it is what it looks like. X times radical 2x. The bottom, again, it's just, I've got a 2x times a 2x that gives me a 2x. Because they're both under the radicals, they'll come out. And at this point, I should cancel my x's, right? You should always reduce your fractions. And so what I've got is this. And is this always positive? Yes, that's always positive. Cool. This one, what do you want to multiply by? I want to multiply by this. See, that's 7, that x there doesn't bother me. Doesn't bother me in the least. So I'm just going to multiply top and bottom by radical 7, and I'm going to get on the top a radical 7. And on the bottom, when you do radical 7 times radical 7, you get regular 7 times x. And I don't have to worry about absolute value bars here because the x was never inside, right? The x was never inside. So the 7 is positive. I know that. Here's another point that I need to make. That might look like it's okay, but it's not, because this is the same as having a radical 1 on top and a radical 2 on the bottom. In other words, this is the same thing as having a square root in your denominator, which you don't like. We might as well just do this right now and get rid of it, right? Do the old multiply top bottom by root 2. Now, root 1 times root 2 is root 2, and root 2 times root 2 is 2. So there's what you got right there. Maybe I'll come down to do this one next. This one down here. What I don't like is a radical 5 in the denominator, so I'm going to do this to get rid of it. What's on top? 5 outside times a radical 5. Looks just like that. Down here, now be careful when you put this together. You get radical 5 times radical 5. This is a 5 times a 2. Right? Don't forget to multiply all 3 of these pieces. Radical 5 times radical 5 is 5 times 2 is 10. Cancel the 5's by the ray. You get a radical 5 over 2. No x's, no need for absolute value symbols. You want to try these two yourself, these two that I left right here real quick. Build your confidence, see what you get. This one. Well, again, I can think of this way. Doesn't necessarily have to be your first step, but this is how you're thinking about it. You're thinking about this as there's a radical 3 in my denominator, and I don't like that. So I'm going to multiply top and bottom by radical 3. On the top, radical 2 times radical 3 is radical 6. On the bottom, radical 3 times radical 3 is regular 3. There she blows. This one. Again, this is the only part you're not comfortable with, the radical in the denominator. So you say, okay, I don't like a root 3 down there. Let's multiply top and bottom by root 3. What have I got on top? Multiply your outsides and your insides separately. I got a 3 outside, and I got a 2 times 3 is 6 inside. That's a 3 radical 6. What have I got down here? I've got a root 3 times a root 3 is a regular 3 times 2 is a 6. And lastly, don't forget about the canceling. Now, I'm not canceling here because one's inside the radical, one's outside. That doesn't work. But here, they're both outside. I can cancel. I'll cancel 3's. That'll give me a root 6 on the top and a 2 on the bottom. There we go. Okay. Whew. That is actually the main part of the lesson. There's just a couple postscripts at the end here. 2 postscripts real quick. So this, I feel a need to mention this because I see this mistake a lot. What have we been doing? We've been doing what I called the factoring rule. So something like if you had well, let me show you a version that has pure numbers in it. If I had like a radical 4 times 9, okay, you could say that that was radical 4 times radical 9. Prove it to you. It's 2 times 3, it's 6, right? Well, if I hadn't done it this way, I could have said, oh, 4 times 9 is 36. But what's radical 36? It's 6, right? So this works for multiplying. It does not work for adding. And I've seen people try it. It's a very common mistake. That's why I'm trying to alert you to it. Don't use it for adding. This is a true statement. It says it's true. Radical 1 plus 4 really is radical 5. After all, the radical is a grouping symbol. You should do what's inside the radical first. So 1 plus 4 is 5, right? I got a radical 5. Can you simplify a radical 5? No, you really can't. So that's what it is. What you cannot do is say, oh, square root of 1 is 1. Oh, square root of 4 is 2. So really, this is a 3. See how that doesn't work? You could not say it was the square root of 1 plus the square root of 4. You cannot do that. Probably where I mostly see it is here. So this says it's false. You cannot say, oh, I'll take the square root of the x squared, and I'll take the square root of the 25, and I'll get an x plus a 5. That does not work at all. It only works for factoring. You have to have a multiplication here. If you want to split the radical over the 2 different numbers, it's only possible if the 2 different numbers are being multiplied. Adding? No, doesn't work that way, so please don't do it. If you see something like an x squared plus 25 in the square root, keep in mind, somehow, however you do it, that there's nothing you can do there. There is absolutely nothing you can do there. There's no way to simplify that. Leave it alone. The last postscript is simply that, well, we skipped conjugates. What's that mean? Conjugates are a special case. So if you ever had something like maybe 1 over 1 plus square root of 2 like this, what we've been doing would not work. You'd say, oh, I'll multiply top and bottom by square root of 2. So I got 1 times square root of 2 on the top. And the reason it's not working is clear right here because you have to distribute these things. You're going to have 1 times the square root of 2, and then you're going to have, it didn't work, right? You still have a radical in the denominator. So just, I'm trying to say don't do it that way. There is a way you can do it, and I'm just pointing this out for, giggles. And it's called the conjugate. So where you had a 1 plus radical 2, you would multiply by 1 minus radical 2, top and bottom. The conjugate basically means change the sign. This was positive, so I used a negative. If this were a negative, I would have used a positive. Okay, so it's just whatever the sign is, you change it. This ends up working. And I could show it to you, but I'll let you work it out yourself if you're curious. We're not going to need that at all in this class, and so I decided to skip it because this lecture was long enough, wasn't it? Sure. But it was healthy. Now you can simplify your radicals, whether they have numbers or, what are you doing to me? Whether they have numbers or whether they have variables inside. You can rationalize your denominators. That's very important. I suppose I should have talked about this part that I said I was going to talk about. What do I mean by simplified radical form? 5 things. All radicals are simplified. Okay. No radicals in the denominator. If you have a radical in the denominator, you have to fix it. That was called rationalizing the denominator. No fractions inside of radicals. So like this thing here, we had a 1 over, well, where did we put it? Not that one. Where is it? This one. We had a square root of 1 over 2. That's not ready. That's not good. That's not simplified radical form. No fractions inside of radicals. Another thing is, like, there must have been a place somewhere where we got something and then we can't, like here, we canceled stuff, right? So all fractions are reduced. That counts as simplified radical form. You got to follow all these rules. So whenever you have a problem that says express in simplified radical form, it means the radicals should be simplified. You should not have any radicals in your denominator. You should not have any fractions inside your radicals. If you have fractions that can be reduced, they should be reduced. And the last thing I'll add here is no negatives inside the radical. And what I mean by that is if you have radical, well, just don't do it. This is actually going to come up in the next lecture when we start playing with cube roots. With square roots, it's not going to come up. But when we start coming up with cube roots, it'll come up. So, but for now, I'll list it there so our list is complete. Okay, we'll do more of this in the next lesson. This lesson was all square roots. The next lesson, we're going to repeat all this stuff, except we're going to do cube roots, maybe fourth roots, maybe fifth roots, higher order roots. Okay, hope that was fun.